Hello everyone, welcome to Exploring Diana YouTube series where we explore the powerful capability of Diana one step at a time. My name is Solmaz and today I want to model one of the tutorials on Diana website. The title is Creep Response of a Pre-Stressed Concrete Beam Under Sustained Load. Let me describe the problem and after that I will jump to the Diana environment to start simulating. In this video, I will simulate a creep benchmark test on a partially pre-stressed flexural beam. This is based on the experiments conducted by Espion and Hallox in 1991. Between 1981 and 1986, a series of partially pre-stressed concrete beams were tested at the University of Brussels. These beams, which were simply supported with an 8-meter span and a rectangular cross section, were subjected to sustained load for 4.5 years. These tests have become a well known benchmark for validating finite element models that study the time dependent behavior of the concrete beam. As you can see on the screen, you can see the geometry and arrangement of the reinforcement and tendon. The pre-stressed tendons in this beam are inclined at a 3.2 degree from the horizontal axis between the load point and the supports. The mechanical properties of material and also the loading history of these tests are shown on this screen. Uh, the mechanical properties of material align with the concrete class C25 and modeled with using the MC 2010 code. At the age of 40 days, a pre-stress load per tendon was applied by post-tensioning at one end. In addition, two concentrated load were applied at a different stage. The first one at the age of 28 and the second one at the age 40, 84. To model this benchmark, I use a three-dimensional finite element model. Solid elements are used for the modeling the beam and the reinforcement are modeled as embedded bar elements. I only modeled half of the beam because of the symmetry. The concrete behavior is modeled by using the MC 2010 and the C25 for the concrete. I also consider the crimp and shrinkage effect for the concrete. Steel plates for load application and support are modeled with the linear elastic properties, and also interface elements are placed between the steel plates and the concrete beam, with high normal stiffness but low shear stiffness. The structural nonlinear analysis is conducted over time steps spanning about 4.5 years. Finally, I compared the experimental and numerical results by looking at the displacement over time. After this introduction, I will jump to Diana environment to start the simulation. Here we go. This is a Diana environment. To start modeling, I need to create project. For this purpose, I will come to the file, new, I call it SPR, and in the analysis type, I only need the structural module. It's a three-dimensional problem. And for the measure type, I want to select hexagonal and quadrilateral measure type. And for the order, I want to select quadratic. For the mid-side node location, I prefer to choose on-shape. And now I need to wait for seconds until Diana create project. Yes. After creating project, I come to the unit and I need to change the temperature and angle. For the temperature, I will select the Celsius, and for the angle, I will select the degree. All is good. To create geometry in Diana, you have three options. The first one is Action Toolbar and using these options that Diana offers you. The second one is Python scripting and using the Command Console. And the last one is importing the AutoCAD file. In this benchmark test, I need to define many details. So for sake of saving time, I will use the second option and create the geometry by Python scripting. And after that, I will explain you each part of the geometry by details. So I will copy and paste Python script in the command console. Wait for seconds, and now we have geometry. In the left toolbar, you can review the detail of the geometry. We have a longitudinal reinforcement, we have a tendon, we have a stirrups, and also you can see the beam, load plate, and support plate. After creating the geometry, we need to assign the material properties to the elements. So for this purpose, I come to shape properties, and I will select the beam as a first step. In the element class, I will select the structural solid. And for the material, I need to define the new material properties. I call it beam concrete is a concrete design code class. And in the material model, I select the fit model code for concrete structures 2010. The aspects I would like to include in my analysis is the shrinkage and creep. As you can see on the screen, there is some predefined input for the fifth model 2010, but I want to choose the C25 for the concrete class, and for the creep and shrinkage, I need to do some modification. For the ambient temperature, is in my benchmark test is 20 degrees centigrade. The notional size of the member is 0.1837. The relative ambient temperature humidity is 60%. The concrete age as a loading is a 14 days that I need to input data in a second is 1.2096 E6. And also the concrete age at the end of curing period is a 1 day. And in a second, it can be considered as 86,400 seconds. That's it. And I will click apply. In the second step, I want to define the material properties for the load plates and support plate. In the element class, I will select the structural solid, and for the material, I need to define the new material properties for these elements. I call it steel because it's steel, and for the material model, I want to select the linear elastic isotropic. So I need to input data for the Young modulus, for the Poisson ratio, and also for the mass density. All is good. In the third step, I want to define the material properties for the passive reinforcement. I have two different passive reinforcement in the geometry section. The first one is reinforcement 8 and the second one is reinforcement 18. Let's start with the reinforcement 8. So for this purpose, I come to the reinforcement properties. It's the embedded bar, and I need to define the new material properties for the reinforcement. I call it reinforcement. And for the material model, I want to select the linear elastic material for the reinforcement. In this section, I need to input data for the Young modulus. The next section is geometry. I call it V8. It's the diameter of the reinforcement. And I need to input the cross-section area of the bar. Is it 5e minus 5. That's it. The second ordinary reinforcement is a reinforcement 18. For the material, I use the previous material which I defined in a previous step, and for the geometry, I need to create the new geometry for the phi 18. Now I need to input the data for the cross-section area of the bar, 0.000254. I will update the material properties, And this last one for the ordinary reinforcement is related to the stirrup. For the stirrup, I use the material which I use for the longitudinal reinforcement. And for the geometry, I call it V10. And now I need to assign the cross-section area of bar to the dialog box of the geometry. Is it 7.85 E minus 5? All is good. After defining the material properties for the ordinary reinforcement, I mean the stirrups, passive reinforcement 18 and passive reinforcement 8, now it's time to pre-stress reinforcement. So for this purpose, I come to the reinforcement properties, same as the previous steps. Type is the embedded bar, and for the material, I need to define the new material property. I call it pre-stress. The class is reinforcement and linear elasticity for the material model. So I put the Young modulus 2e plus 11. And in the aspects that I want to include in my analysis, I want to select the bonding. By activating these aspects, the reinforcement is not bonded to mother element in order to have a post-tension load. And the next step is defining the geometry. I call it pre-express again. And in the section cross-section area, I need to input the cross-section area of the each tendon. 9.3 E minus 5. That's it. All is good. Now I will click on Update to create these material properties. After defining the material properties for the all elements in the geometry toolbar, now it's time to move to the next step. I want to introduce the interface between the loading plate, support plate, and the main beam. So for this purpose, I come to the connection. I call it interface. The connection type is also interface. And for the source face and target face, I need to hide the beam geometry and select the faces of the load plate and the support plate which have connection with the main. And for the target faces, I need to select the faces of the beam which are in connection with the support plate and the load plate. In the element class tool dropdown, I want to select the structural plane interface. For the material, I call it interface. Material model is a nonlinear elasticity. Now I need to input the data for the normal stiffness and shear stiffness in the x and the y direction. So I need to consider the very high stiffness, 3.2 E13 for the normal direction, and the low stiffness for the low shear stiffness in the x and y direction, 3.42 E5. Also for the y direction, 3.42 E5. And for the nonlinear elasticity, I select the no tension with the shear stiffness reduction. So based on this selection, I have to input data for the critical interface opening for the reduction. I consider E minus 6. I also input the same data for the reduction for the first shear and the second shear direction. Okay, that's it. Everything is good. Now I come to create and create this connection and assign it to the model. You can see the blue dot and the red dot that show the connection between the main beam and the support plate and load plate. So let's set the boundary condition for the model. First, I want to restrict the translation in the z direction along the bottom edge of the support. So for this purpose, I move to the left view to have a better access to the bottom edge of the um, support plate. Next, I come to the support and call it support Z. Now I need to create the support set. I call it only support and add the to support set. I target type is the edge and I select the bottom edge of the support plate. And after that, I fix the T3 in the translations degree of freedom. I create this support. After that, I need to fix in a Y direction. So I call it support Y in the support set. And in the vertex, I select the one vertex in the support plane and fix the T2. And finally, uh, since I have using the symmetry model, so I need to restrict the translation in the x direction on the symmetry surface. So I move to the isometric view, and now the target type is face. I select the symmetry face and fix the T1 on this face. Great. So let's continue by assigning the load to the model. The first load that I want defined to the model is a self-weight load. So I come to the global load. I call it SW. I need to define the load case. I add the SW load case and I come to the create. In the next step, I want to assign the post-tension load to the model. This post-tension load is applied to the one end of the pre-stress tendon. So I come to the geometry and I show the pre-stress tendon and hide the rest of the geometry. You can see the tendons on the screen. After that, I come to the load. I call it post-tension. And also, I need to define the load case for that. That's it. The load target type is a shape, and the load type, I need to select the post-tensioning load. You can see the two different boxes on the screen. For the first box I need to select the loaded reinforcement. So I select the tendon. The tension type is a one end. So in the next box, I need to select the end of the tendon. Very good. Nodal anchor force is 122, 800 Newton. And we don't account for any pre-stress losses. So I consider the zero for the anchor retention length, and the Coulomb friction coefficient is zero. I come to create, and now I apply the post tension to the model. The last step in the load definition is the applied load. So I want to define the distributed load on the top surface of the loading plate. For this purpose, in the first step, I come to the geometry and I will activate the beam element, loading plate, and support plate, and deactivate the pre-stress reinforcement. Very good. And after that, I come to the load. I call it load. And also, I need to define the new load case. Very good. And the load target type is a face, and the load type is distributed force. The loaded face is the top surface of the loading plane, and the value is minus 19,607. This distributed load is equivalent to the minus 1 kilonewton at the center of the loading plate. So by dividing the minus 1 to the area of the loading plate, you can see the result same as the value that we input in the phase force value. So after that, I come to the create, and now we set up the all load to the model. After assigning the all desired load to the model, now it's time to define the load combination and time dependent factor. So for this purpose, I come to the load toolbox, and I will click on the combination. For the first combination, I only need the self-fit and the post tension. And for the second load combination, I only need the distributed load. Once load combination are created, I can no longer use individual load cases for the analysis. So I only need two load combination, and any extra load combination must be deleted. So I will delete the load combination 3. That's it, very good. Now I want to define the time dependent factor to each of the load combinations. So I come to the time dependency factor, and for the time and factor, I only need copy and paste data from Excel very easily and very quick. I bring data from the Excel. That's it for load combination 1, and also for load combination 2, I will bring data from Excel and copy and paste data to the Diana environment. Very nice. I come to the OK. And now I assign the and define the load combination and its time dependent factor. In the left toolbar in Diana environment, you can check what you have done from the beginning up to now. We define the geometry, we assign the material, element geometry, supports, loads, connection, interface, and at the end, we need to the mesh properties and generate mesh. At this step, we are only one step behind the analysis setup. So I come to the mesh properties. I will select the beam, support plate, and loading plate. The type, the seeding method is the element size. And for the element size, I will input the 0.1 meter for the desired size. I come to the apply, and after that, I will generate mesh. Just wait for a second. And after that, you can see the very beautiful meshed model. After generating the mesh, we need to set up the analysis. To save time, I have already set up and run the analysis in a separate file. I also have the results ready. Now I will show you the file and explain the analysis setup, and we will review the result together. So, at first I want to explain the analysis setup. In the left toolbar in Diana, you can see the analysis is a structural nonlinear analysis, and also we need the time step executed block. In the time step, the step that I use is smaller at the beginning, where the creep behavior is more significant. And as the analysis progress, we switch to the larger step until the end of the 1642 days. If I want to explain to you the step, we have a result at the first day for 2 days, and after that, we increase the time step until the 1400 days, as you can see on the screen. Okay. Now I come to the results panel in the right side in the Diana environment. And the first result that I want to check is a displacement in the Z direction. So for this purpose, I will show you the contour at first step. And after that, in the selection mode, I will define the node selection. And I want to see the displacement in the Z direction in the middle of the span versus time. So I come to the table, and as you can see on the screen, we can see the displacement in the Z direction during the different time step. Let me bring the real comparison between the experimental and numerical result to you. Okay, as you can see on the screen, to compare the result with the experimental data, we only need copy and paste the displacement from Diana to the Excel. and it's very easy and convenient. After that, if I want to compare the result overall, the numerical result align with the experimental data, particularly during the post-tensioning stage and after the first load application. However, after the second load increment at 84 days, the numerical model start to deviate slightly, showing a stiffer response rather than the experiment. The cause of this deviation is that the model doesn't account for the cracking in the numerical simulation. To simplify the simulation and this model, experimentally cracking was observed after the second load increment, as well as we will see in the stress result. This was also reported by Espion and Halux in 1991. The next result that I want to review is a crack index FATU immediately after the second load application at the 84 days and also at the final stage of the analysis. The crack index FATU is calculated by dividing sigma 1, the tensile stress, to FAT, the tensile strength. The area with FATU greater than 1 indicate a risk of the crack. Just let me change the viewing type, element set. Yeah, that's it. This is the FATU at the final stage of the analysis. And let me show you the time step 100, where the second load is applied to the model. And after the second load application, the beam shows cracking, which explain the difference between the numerical and experimental result, which are observed at this video earlier. At this moment, this tutorial is finished, and now I want to show you how you can find this tutorial on Diana website. Just let me open the one browser. In Diana website, please go to Get Started section, Tutorials, and in based on tutorial type, analysis, and model picker, you can for your desired document. For example, for this tutorial, I come to the technical structure. The analysis type is a structural nonlinear, and the model required is a expert structure. So that's it. You can find the creep response of a pre-stressed concrete beam under a sustained load tutorial. Thank you for your attention. Please subscribe to Diana YouTube and don't forget to tune in for the next video.